Hello friends, my name is Vivek Sharma. Today we can cover this interesting problem that's called minimum depth of binary tree. So in this problem we have been given a binary tree and we need to find its minimum depth. And as per this problem statement, minimum depth is the number of nodes along the shortest path from the root node to the nearest leaf node. Okay. Leaf node is of course a node that does not have any children. So let's do this. Let's try to understand this problem from this whiteboard. So this is root node and this is one leaf and they are another leaves, right? Because they don't have any children. So 9 does not have any children and 15 and 7 does not have any children, right? So these two nodes also don't have any children. All right, so in this binary tree there are three leaves. So what we need to do, as per the problem statement, we need to find the number of nodes along the shortest path from the root node to the nearest leaf node. So this is root, and shortest path, we can see that this is the shortest path. So in this case minimum depth will be 2 because number of nodes is 1 and 2. Okay, and if we follow this path, then the number of nodes will be 3, right? So 3 is not minimum because 2 is minimum, so we will return 2. And if we follow this path, then also number of nodes will be 3, 1 2 3. Okay, so this is the problem. Now how we are going to solve this problem? This is definitely very intuitive for the recursive approach, top to bottom. Why? We can start from the root node and then we can go down, traversing left and right. And in this case, what we can do, so let's say we start from root node, okay, and we have the base condition that once we find root equals to null, means if there is no child, means if we hit any leaf, then we can return 0. Okay, so we will traverse for the left side first and we got 9. So 9, and then it will check root dot left is null, root dot right is null, right? Then it means we hit the base condition. So in recursion we always have the base condition so that we can get out of the recursion. Okay, and another way is, if we don't want to use the recursion, we can use the iterative method as well, iterative version, and in that case we can use the explicit stack, right? So in fact, in recursion also we use the implicit stack. So let's go ahead and try to understand how this will work in the real time. So once we have this root, we will start from the root and we have this implicit stack. Okay, so if we have this implicit stack, we will insert 3, or we will push 3 to the stack, and then we go to the left side, we will push 9 to the stack, and then we will say okay, root now 9 is the current root, means the current node, and this 9 does not have any left or right child, means left and right both are null, right? Because it is the leaf node. So what we can do, in the base condition we can return 0. If root equals to null, then we can return 0. So let's quickly do here as well, so that picture will be little bit clear. Okay, so if root equals to null, we are saying that we will return 0, and we will say the here int left, this is minimum depth, so left side, this is in fact left side depth, and similarly int right, this will be the right side depth. Okay, and we can simply do return math dot min left comma right. So this is the code we are thinking, right? So if we hit the base condition, then we need to return 0, right? Otherwise we will calculate like for the left height and the right height, and then these left and right, they will return something, some height, some depth to the root, and the root will be the decision maker. Then it will decide, okay, whatever the minimum of left and right, that will be the minimum depth and that will be the output, right? So let's traverse through this way, right? So 3 is there, 9 also we pushed here, right? And then it hit the this base condition, root equals to null, then it will return 0. Okay, so 0 means root equals to null, so it hits this condition and then it returns 0 here, right? And see this code, so this return 0, we are not doing anything, it's still minimum depth, right? So uh, there is a way to accumulate, I mean we need to accumulate this 0, right? Because here we need to calculate the number of nodes, so this we still hit the number of node, that is 1. So what we need to do, we need to add 1 here. right? So now it will be 0 plus 1, so the depth will be 1, right? So our code will be something like this: 1 plus minimum depth. Similarly for right, 1 plus minimum depth, right? Because remember, the problem statement is saying minimum depth is the number of nodes along the shortest path. So base condition gave us the 0, right? And we need to include 1 as well. We need to add 1, so we will be adding 1. Okay, now this 1 we will be passing to 3, right? And similarly 3 will be adding 1 as well, so 1 plus 1, that will be 2. So 3 now will be having 2 from the left node, right? So this 9 will be returning 1 to 3, and then 3 will be doing 1 plus 1, that is 2. Okay, so now left traversal is done. Okay, why 3 will be doing 1 plus 1 equals to 2? 1 plus 1 equals to 2 because this left will be returning to recursive. Now let's see this. This is the implicit stack, right? Implicit recursion stack. We started from 3 and then we came to 9 and then we hit the base condition, that is root equals to null. Root, what is root here? Root dot left is null and root dot right is null. So this is base condition. So now the recursion from the base condition itself, we are returning 0, returning 0 to 9. So we are accumulating 0 plus 1, that is 1, and then now from the recursive stack we are coming out. So now it will be returning 1 to 3. Now 3 will be having, so now we popped 9, right? Now 3 is having 1 plus 1 equals to 2 because still we are executing the same code, right? Left equals to 1 plus minimum depth, but this is we are running the same code. Earlier we were running for 9 and now we are running for 3. Okay, now we need to traverse the right side, right? So what we will do, we will push 20, right? And everything, this is happening behind the scene. I'm here just explaining that how this recursion and everything is working behind the scene. But for the code, for recursion is doing all this thing for ourselves, right? So we don't have to do all this thing manually, but this is just to understand the concept that how this is going to work. So now we will be pushing 20 because left is done. So left side is completely done. So now it will be going to the right side, root dot right. So root dot right, and then after root dot right it will come again minimum depth, and then it will say, okay, is root null? No, root is not null. Then it will go again left side because root equal to root dot left here, right? So now it will go root dot left. So after 20 we will be pushing 15. Now it hit the base condition again. So because left and right is null. What is base condition? Base condition is this: if root equals to null, then we are returning 0. So returning 0 means we are returning to 15, right? Now 15, what 15 will do? 0 plus 1, right? And then 15 will pop up from the stack and it will return 1 to 20. Now 20 will be again accumulating this, and then 20 will be doing, 20 will be adding 1 as well. So 1 plus 1 equals to 2. So now 20 will be having 2 here, right? And now 20, this left traversal is done for 20. Now 20 will do the right traversal. So it will just go to 7. It will post to the recursive implicit stack to 7 in the stack, right? And the 7, it will hit again the base condition because 7 is the leaf node. So now this base condition will execute and it will return to 0 to 7. So now see what 7 will do. 7 will do 0 plus 1. So it will also do 1. It will add 1. And it will pop 7, and then 7 will return to 20 itself, right? So 27 will return 1 to 20, and 20 will do the same thing. 1 plus 1 equals to 2 for 7 as well. So now 20 is having two choices, right? It got 2 from 15 and it got 2 from 7, right? And now it has to decide, okay, what is minimum out of these left and right, right? So once this left and right is there, right, traversal is there, then we need to decide, okay, what is the minimum of left and right? So it will decide, okay, out of 2 and 2 there is no minimum, right? So 2 is still the answer, right, for 20. So 20, it will return 2 to 3, so it will pop 20 and 20 will return 2 to 3, right, in the recursive stack. So now 3 is having 2 and 3 will again add 1 as well. So 2 plus 1 equals to 3. Now 3 is having two choices. So 3 got 2 from this left subtree and 3 got 3 from this right subtree, right? So we have this code, right? Minimum of left and right, right? Minimum of left and right. So now in that case, what is minimum? Either 2 is minimum or 3 is minimum. So 2 is minimum, so it will return 2 as an output, right? That's what we are doing here. Math.minimum left and right, whatever the minimum. So every node itself is adding 1 here, right? So if it is returning from somewhere, then it is increasing 1 for left and increasing 1 for right, so that we can include that node itself, right? After base condition is hitting, right? So after we hit the leaf, then it is getting 1, so we are including that node itself and we are returning to its parent. Similarly for 7, 15, 20, similar thing we are doing. Once parent get the uh, result from left subtree or right and right subtree, then it's deciding, right? It's deciding, it's executing this logic, minimum left or right, whatever the minimum, and that whatever the minimum is there, it's returning to its parent itself, and then parent is also decision maker, right? So every node is increasing 1 by default. So once it get 2 from this 20, then it's adding 1 as well. So 2 plus 1 equals to, it's doing 3, right? This one. So 3 is doing the same thing. It will pop, and now it will make the decision because the whole subtree traversal is done. Now 3 will decide, okay, what is the minimum out of the left and right? Whatever the minimum, that will be the output. So this is the recursive approach. Now here we need to consider one edge case as well, but let's first of all try to run this and let's see if this is getting compiled. So this is getting compiled. Okay, now let's consider another binary tree. So let's say for example, we are having the binary tree something like this, 1 and then 2. This is the left. Okay, so this is the binary tree, and if we run this here, then what is going to happen? Let's see. So 1 comma 2, and if we do tree visualizer, then this is the exact tree, and if we will run, then this is going to give the wrong answer. Output is 1 but expected is 2, right? And that makes sense, right? So nodes are 2 here, but our answer is giving 1. Why it's giving 1? Let's try to understand this. So again we will use the recursive stack. So 1 is there, right? We will start our traversal from 1. We will push 1 to the stack. Generally we use the push and pop to the stack. This is just the naming convention, and insert and delete for the queue, or offer or poll from the for the queue terminology for the queue data structure. So this is just the naming convention, but otherwise we are just inserting itself. So 1, we started from root, and then we will check, okay, left, so left is there 2, and after 2, left and right is null, so we hit the base condition, then it will get the 0 from the base condition, and then it will add 1 as well, right? So whenever we hit the base condition, we are accumulating by 1, we are increasing it by 1, so that we can include that node itself. So now 2 got 1, right? And after 2 will pass 1 to 1 itself, so 2 will be popped out and it will return 1 to the 1, and then 1 will have now 1 plus 1 equals to 2, because every node is increasing, right? So it got 1 from this left subtree, and then it will increase by 1, so it will be 2. Now similarly it will traverse the right subtree as well. So right subtree is null, so means it immediately hit the base condition, right? It immediately hit the base condition because right is null, so right side will return 0 to 1. Now what 1 will do? 1 will do 0 plus 1 equals to 1. So now from right subtree it got 0 plus 1 equals to 1, and then from left subtree it got 2, right? And now we will calculate, okay, what is the minimum out of left and right? So minimum is 1, and that's why our output is 1, right? So as per this logic, our output is correct, but for this problem this output is wrong, right? So our code is working as expected, right, like this way, but as per the problem statement it should be 2, because the number of nodes are 2. So in this case we can handle this case in the if else. So we can check, okay, if the right subtree is null, right, if it is having the right is null, then we can return only the left height or left depth. If left is null, then the same case we can return the right. So that's what we can handle this, and then this problem will be solved. So let's go ahead and do that. So what we can do here, so after calculating left and right, we can check if root dot left equals to null, then go ahead and return right. Okay, Else if your root dot right equals to null, then go ahead and return left, right? So we just walked through this tree, right, that is having the left and right is null. Similarly we can have this situation as well where left is null and root right is there. So similarly what we need to do in this case, if left is null, we need to return whatever it's coming from right, right? So from the right it is coming 1, and then 1 plus 1 equals to 2, so the output will be 2 because every node is including itself, right? So we don't need to consider this null thing because null thing itself is returning 0, and then we are accumulating 0 plus 1 equals to 1, and that's where the problem is happening. So what we will do, if we will hit this kind of condition, if root dot left equal to null, return the right side. If right is null, then return the left side. So let's go ahead and check this. So looks like now this is working fine. Time complexity wise, it will be order of n, right? Because in the worst case, if the tree is like a skewed tree, like let's say for example like this, it looks like a linked list or something, we need to traverse each and every node, right? And in fact, even if it is not skewed, we are going ahead with the each and every node because we need to calculate the minimum depth, right? So in this case what we are doing, we are checking this and then we are calculating this is the left, and then similarly we are going to the right side and then we are calculating, okay, this is the right number, and then we are doing the minimum, whatever the minimum of left and right, and that's what we are deciding. So in the worst case, basically it will be order of n, and space complexity will also be order of n because it might not be the I mean, in the worst case, we will be traversing each and every node, and we can see like in the implicit stack we are maintaining. If you will see very first page here, so see here 3 9 20 15 7. So we are just storing internally all these nodes, right? So it will be order of n space complexity wise. So let's see, looks like this problem is working fine, whatever we discussed so far. So this is like recursive approach. Now the second approach I wanted to quickly go through is the depth. This was the depth first search because it was recursive. Now the second approach will be the breadth first search. How we can use the breadth first search here? We can take the queue data structure, and in the queue data structure we can start from the root, and the same concept here as well, right? So we will be, apart from stack, what we will do here, we will be taking queue, right? So this is the queue. Okay, we will be starting from 3. We will be inserting 3 to the queue, right? And then we will be polling 3 from the queue. We will be checking, okay, root dot left is null, yes, then we will insert this, and root dot right is null, yeah, root dot right is not equal to null, then 20. And similarly root dot left is not equal to null, then we inserted 9. Root dot right is not equal to null, we inserted 20. And then we will be checking, okay, what about 9? So is root dot left is null, yes, root dot right is null, then yes. So this current node is root right now, right? So when I'm saying root, it means I'm talking about 9 right now because I'm on the root. I'm on the 9, right? So if it is the leaf, right, so 9 is the leaf, then what I can do, I can return immediately the label, which label I am. So this is the first label and this is second label. So in this case return output will be 2. So you can say like I am here saving, I'm not traversing the whole right side tree, I'm just going through the left side and then just immediately returning. So that way we think like this is like maybe like little bit what we are doing, we are just trying to save the traversal, right side traversal, but it really depends upon the tree, what kind of structure we have been given, right? If we have been given the like full valence tree itself, like 9 is also having some node 7 9 or whatever, then in that case we have to go through each and every node, right? So it really depends what kind of the example we are going through. Now let's quickly make our hypothetical example, and then let's do that as well. Let's say 3 and then 9 1 and then 3, and then similarly let's do 5. Okay, so this is some one hypothetical tree, and similarly we will use here as well queue. So we will start from 3. So 3 is there, we inserted in our queue, we polled 3, and left and right is not null, left and right is not null, so we will be inserting 9 and 1. So we inserted 9 and 1 here, we polled 9, and then we saw, okay, left is not equal to null, so 5 we inserted here, right? And then for 1 also, right is not equal to null, so 1 we polled, and then we inserted 3 as well. So this only the 3, and then 5 we polled, and then we saw okay, left and right is not equal to null. So in that case, what we will be returning, we will be returning labels. So this is first label, and then queue size is here 1 and 9, so it will be second label, right? So one label, second label, and that 5 and 3, it is the third label. So once it hit this condition, if root dot left and right is not uh, root dot left and root dot right, they both are null, means it is the leaf condition, then basically go ahead and return these steps or labels, whatever the labels we are so far, right? So in this case, label is 3. So first label, second label, and third label, right? So I hope this is clear. If it is not clear, let's quickly code this, and then I think it will be pretty much clear. So I'm just going ahead to erase the earlier code, and then let's take the queue here. Queue is type of tree node here. Queue equals to new linked list, and queue dot offer. First of all, we are inserting root here to the queue, and then if queue is not empty, right, then what we are going to do here, we are taking the size of queue. Why we are taking size of queue? Because how many numbers are there in the queue, that's the number we need to process. And once this processing is done, we can increment our label. So initially label is 0, then we will be incrementing label is 1. Similarly, if 2 elements are there in the queue, we will be incrementing 2 label, and then 2 elements are also there, then we will be incrementing 3 label. And once it will hit this condition, then we will immediately returning 3 as our output, right? So that is the idea. So let's go ahead and do that. So integer I equals to 0, I is less than size I plus plus, tree node equals to queue dot poll, and if node dot left is not equal to null, then queue dot offer node dot left, and if right is not equal to null, then queue dot offer node dot right, right? And also here, also check after polling if left and right both are null, right? Node dot left equals to null and node dot right equals to null, then go ahead and return label or depth, right? So depth, what is depth? We can take another variable here that's called depth here, and we can go ahead and insert here. We can increment, actually not insert. So let's increase that depth itself. If it did not find anything, return -1 or 0, it does not matter, right? So it should hit this condition, right? Root dot left equal to null, root dot right equal to null, and we are incrementing depth upfront so that it will have the updated value, right? So once we are entering this loop, we are already up incrementing this. So once it will hit this condition, then it will be having the updated depth. What does that mean? 3, if it is entering to the 3, we are having the depth 1 ready, right? Similarly, if it is hitting like 9 and 1 this level, we will be incrementing upfront 2. Similarly, if it is hitting like 5 and 3 this queue size, then we will be having upfront 3 depth because we are incrementing it beforehand here. And once it hit this condition that okay, left and right both are null, then what we are doing, we are going ahead and returning 3. So 3 is our output in this particular case, right? So 3 is our output. Okay, so that's what we are doing. Let's quickly check this as well. So variable might not have been initialized, and that makes sense. So depth is 0 here. And also another thing is, let's take care of if root itself is null, right? Then we need to return 0, right? Because if root is null, then the minimum depth will be 0. Time complexity will be same, order of n, and space complexity will also be same, order of n, because we only change the data structure here. Earlier we were taking implicit stack in the recursion. Here we are taking explicit queue, but the idea is same. So in the worst case, we have to store all these nodes, right? Space wise also we are order of n, and complexity wise also we have to traverse each and every node in the worst case, right? So now let's check other compilation errors. If there is not any, then let's go ahead and submit this. So looks like this concept is also working fine. So before ending, we learned so far the two approaches here: minimum depth of binary tree. One's the recursive approach, and another is the this BFS, breadth first search. So another is the depth first search, and this is the breadth first search. So this is the two approaches that we have learned so far. So in the depth first search, we were taking here the implicit stack, right? We were taking the implicit stack, and then implicit stack we were starting from the root node, and we were just going left and right. And once we hit the base condition, then base condition was returning 0, and then we were accumulating at every node level so that we can count that node itself. And the left subtree, once this root is getting, the left is L and the right is R. If it is getting left L and R, then this root is decision maker, basically what is the minimum of left and right, and that is the output. Similarly, whatever we are doing in the queue, in queue also we are doing the similar thing here. So if we will go to here, so in queue also, like if it is a bigger tree, or it might be any tree, right? But this was like I was taking some worst case, like little bigger tree, right? So we are starting from the root, and then we are storing this root to the queue. We are going similarly left and right. If it is not equal to null, we are inserting that to the queue. At every level we are incrementing our label as well. So once we hit this condition, if root dot left and right both are null, we are returning this depth itself, whatever label we are incrementing. So here naming convention is depth, but in fact this is the label, right? So these are the label order traversal. This is label 1 2 3, something like that. Okay, so I hope this might be useful. Thanks a lot. Have a good one. Bye.